In this problem, we're going to take a look at a certain set of problems referred to as mixture problems that give rise to first order differential equations. In fact, again, these will be linear, so we kind of know where we're headed as far as solutions are concerned, right? So let's describe this problem, and it will take a little bit of time to describe what's going on and to then derive the relevant equations. But the mixture problems, they're also sometimes referred to as a compartmental analysis. And so you have a compartment. In this case, I'm going to say, suppose we have a tank, right? And I'm going to draw some stuff there. And then draw some stuff there. So we have a tank, and what's going to happen? Well, initially there is some amount of a fluid in this tank, or maybe I should stick with the concept of a compartment, right? So you have some kind of fluid here. It could be a liquid or a gas at initially. And then at a certain time, you turn on a pump here and another pump here to where we're going to be pumping stuff in. And then that stuff will be well mixed. So let me draw. So it's going to be well mixed. And then we're going to pump some stuff out, right? Okay. Well, let me be a little bit more precise, right? So we're going to pump a liquid in that may or may not have a certain substance dissolved in that liquid. And just to simplify the derivation of this, let's say we have water and salt, right? So a mixture of water and salt, that would be some kind of brine. So you might have a certain concentrate being pumped in at a certain rate, and then it's going to be well mixed, right? And then that well mixed mixture will be pumped out, possibly either at the same rate or maybe a different rate. What are we interested in? Well, what we would like to get now, as a function of time, we would like to know how much salt, or in general, how much of whatever that substance is that is dissolved in our medium here, our fluid, how much of that substance is present at any given time, right? So that's kind of the setup, right? You have a tank, you have something flowing in, something flowing out. Things are being well mixed, and we want to know at a specific time, once we turn those pumps on, for t greater than or equal to 0, how much of that substance is present, right? And we're going to end up getting a differential equation because it's going to involve a rate of change, right? Now, technically, there are two quantities of interest here. First, so let's define all these things that we're going to need. So I'm going to start with the two big functions. So V of t is going to represent the volume of the fluid, right? So it could be the gas or a liquid. So this will be the volume at time t. So how much of the blue stuff is in the tank at any given time? Is it close to full? Is it close to empty? What's going on, right? A of t is going to represent the amount of the substance in the tank at time t. Again, could be like salt, or it could be a dirt, some kind of impurity or something like that. So this is the amount of substance in the compartment, right, at time t. All right, so those are the two big functions. Okay, so let's define some specific numbers now. So V of 0 is going to represent, as you might expect, the initial volume. So how much, liquid or gas, how much of this fluid is present the moment we turn on the switch to this pump, right? So V of 0 is the initial volume. And I'm not putting any units right now. I mean, you have a variety of units that can be used to measure these things. And then, of course, A of 0 will be the initial amount of substance, right? So the initial amount of the substance. Now, what if there is none of the substance present at time 0? Well, then that initial amount will be 0. All right. So that's kind of the right. So that's the setup there, and then let's see. So now, as far as what is going in, right? So as far as what is going in, I'm going to use R sub in. So R in is going to represent the flow rate of the entering liquid, right? So this represents flow rate of the entering liquid, right? And then C in is going to represent the concentration of the substance in the entering liquid. So this is the concentration of substance, right, in the entering liquid. So for instance, let's say if it's a brine, it might be something like, 2 pounds per gallon or something like that, right? That would be the concentration. And then, so that's R in, and then that's C in. Well, you'll have something similar. You'll have R out will be the, this will be the flow rate of the leaving liquid. So going out here, right? So this of the leaving liquid. And then finally C out will be the concentration of the substance in leaving liquid. Substance in leaving liquid. Right, so we got lots of things here to keep in mind. We have the overall functions, and then we have some initial constants, and then some rates and some concentrations, right? So what is the overall principle here? So let me write it here, and I should be able to get it fixed. So the overall principle is the rate of change of A, right, which is the amount. So A prime of T is going to be equal to this. Very simple principle. The rate at which A of T, the amount, enters, right? So how fast is that amount going in here, minus, right, the rate at which rate at which the amount leaves, right? Right. If we're looking at the rate of change, then we're going to look at how fast is that substance going in versus how fast is that substance leaving. All right. So let's see if we can break down each of these. So in fact, let me just refer to this as I, and then this as 2I. So what is I? Well, if we think about it, so just as an example, let me put a couple units on these things. So, let me use like pounds, gallons, and minutes. So your flow rate might be in units of, let's say, gallons per minute. And then it would be the same thing here. This would be, again, gallons per minute going out. Right, so that will be your flow rate. And that has to do with the volume, right? The rate of change of volume, right? And we're going to get to the volume. The volume equation is a lot simpler, so I'm going to leave that towards the end. The concentration would be in units of, let's say, like I said, it might be pounds per gallon, right? So for each gallon of, let's say, water, how many pounds of salt is dissolved, right? So that would be your an example of your units for concentration. And then the same thing here, right? Pounds per gallon. So if I want, and this is the stuff going in, right? This is the stuff going in. So if I want to find an expression that will give me the rate at which the amount enters, so I'm looking for something that would give me, so the amount would be, let's say, in pounds, and then the rate would be, like meaning per minute. So if I look at the units for the rate in, it's gallons per minute. If I look at the units for the concentration in, that's pounds per gallon. If I multiply these two rates, the gallon actually goes away, and I will be left with pounds per minute. So that would represent the rate at which the amount enters. So I is simply R in times C in, right? And again, if these two things are constant, then yeah, this is just going to be a constant. So that's pretty straightforward. And well, we can apply that same principle to figure out expression 2 here. It's simply going to be the R out times the C out. But the problem now is that C out is not a constant. Because the amount in the tank is necessarily going to change, right, over time, then it means the concentration in the tank is going to change as well. So we have to take a look at C out a little bit further. So we realize that, hey, okay, in principle, these are going to be constants, right? But the C out isn't, because the concentration of the substance in the tank at time t is going to be, again, the amount that's in the tank at time t divided by the volume of the fluid in which it's dissolved at time t. So this is C out, right? And we can see where our unknown is coming in, right? So there we have it. Well, so we have these two pieces, and we're going to put it all together in a second here. Let's take a look at V of t now. Let's see what we can come up with V of t. Well, that's a little bit easier, because the volume, you'll have an initial amount, and then you're adding more of this liquid at a rate, per unit of time. So the volume in the tank at any given time is going to be that initial amount times the rate in minus the rate out, right, times t, right? So we've essentially solved for one of our two big functions. It's the volume function. There's not much to solve. It's always going to be a linear function. Sometimes it might be a constant, right? But you have your initial amount, And then essentially, this is your net change over the whatever time interval, right? For a certain amount of time, right? So that's your volume function. So let's put this all together now to see if we can write down the differential equation for the rate of change of the amount, right? So putting this all together, we get that, and I'll write this as dA dt, right? So that's this. The rate at which the amount enters is Rn times Cin minus the rate at which it goes out is going to be R out. So we have that constant times. Now, I'm not going to write down the C out anymore. I'm going to write this expression. So the concentration going out is the amount going out divided by the volume. But then I'm going to put the formula for the volume right here. So the denominator here is going to be a little bit lengthy, but there we go. And then we have plus the R in minus R out times T, right? And there we go. So let me box this off. And this is our differential equation for our single compartment mixture problem, right? And the whole idea is that the mixture in the tank is going to be completely homogeneous, and there's no other process going on that would either create or destroy the substance. So it's again, this is a physical expression of another conservation law. We're not creating any of the substance. We're not destroying any of the substance. We're essentially just changing it. We're homogenizing it and then expelling it from the compartment. All right. So there we go. So let's take a look at an example of this and see what will happen. Okay, so what I will do, instead of writing down a paragraph, I'm just gonna read something and then just write down the relevant bits of information, right? So let's see, suppose we have a tank that contains 100 gallons of a solution. So that's, I'll write this down. So V of 0 is 100 gallons. Right, so that's our initial volume of dissolved salt and water, which is kept uniform by stirring. If pure water is allowed to flow in, so pure water means your C in is 0, right? So at a rate, let's see, so C in, so this would be, so it's in pounds, so let's say pounds per gallon, right? Is allowed to flow into the tank at a rate of 4 gallons per minute. So that's our RN. So 4 gallons per minute. Right. And again, it's well mixed. And then the mixture flows out at a rate of 3 gallons per minute. So we have our R out is 3 gallons per minute. 3 gallons per minute. And then it says how much salt will it be in the tank after T minutes. So this is A of T, that's what we want. If 15 pounds of salt are in the mixture initially. So that means A of 0 is 15. So 15 pounds initially, right? We're not, so basically the way you can sort of interpret this problem, maybe it's a situation where you had a chemical process going on and one of the substrates was salt. So yeah, and it's dissolved in 100 gallons of liquid. And what you're trying to do is like you're trying to flush this compartment or this container completely clean, maybe to run another chemical process. So that's why you're pumping fresh water in. So the whole idea is you're trying to flush this compartment completely clean of salt, right? And one of the things now I won't do all the algebra and stuff in this particular example, but one thing you could ask yourself is how long would the model take to then guarantee that you have no salt left in the tank? So like how long should you continue the rinsing to get it, clean, or at least to get it to a certain level where it can be considered clean for further use. All right. Okay, so let's start by writing down the volume function. So our V of t is the initial volume plus the rate that's going in minus the rate that's going out times t, right? And the reason why we can simply multiply by t is because these are constant rates. So essentially, this is the function that will define the amount of water in this tank. So it is 100 plus the quantity 4 minus 3t. So it is 100 plus t, right? So that's our volume function. Now let's write down the differential equation that when we solve it will give us our amount function. So dA dt. So again, I'll put all the pieces in and simplify wherever needed. So the rate in times the concentration in, right? So essentially no salt is going in the tank, right? And then minus the rate at which it's going out. So that's the rate out is 3. And then the concentration going out is however much is in the tank at that. Well, I can just use A. Let me just use A. And then that's divided by the volume in the tank at time t. So this is the amount divided by the volume. And there we go. And then I'll restate the initial condition. So A of 0 is 15. All right. So let's see how we would go about solving this. So let's simplify. So dA dt is equal to, and what we have here is negative 3a over 100 plus t. Oh, I don't need to restate the initial condition, but that's the differential equation, right? And it turns out that this differential equation is both linear and, in this case, it is separable, right? Because in the numerator only there is a function of a, and then in the denominator on this side only a function of t. So this is separable. It is also linear, right? It's also linear. In fact, I think I want to treat this as a linear one, and just because we haven't done too many examples of linear ones where our q is 0. Because see, if I do this, so if I write this as dA dt plus 3 over 100 plus t times a equals 0, right? Because of this, right? That goes away. Then yeah, I can see that this is linear, right? Here is my p of t. Here is my q of t. And when I look at this, another thing that you could keep in mind is like, how difficult would it be to integrate, something like this? Well, it's not going to be too bad. So I think let's go ahead and use our integrating factor method, because again, this is a linear differential equation. So mu is e to the integral of 3 over 100 plus t dt. So this is going to be a ln, right? Because we're going to have e. We would factor out the 3, and then the antiderivative of 1 over 100 plus t. That's going to be the natural log of 100 plus t. And then we know this is going to simplify. Look, so I'm going to take up the 3, and this is e to the ln of 100 plus t to the third power. And then properties of e and the natural log. This simplifies to 100 plus t to the third power. So that's my integrating factor, right? So now we're going to multiply both sides by the quantity 100 plus t cubed. So this is what the differential equation becomes. So 100 plus t cubed times dA dt plus. Now, when I multiply this term by my integrating factor, since I have a 100 plus t in the denominator, it will reduce one of the factors of 100 plus t in the integrating factor. So I'll be left with this 3, and then I'll be left with the quantity 100 plus t squared times a. And look, I'll still have a 0 on this side. So the fact that I have a 0 on this side, it means my subsequent integral, the second integral, is going to be super, super easy. I mean, what's easier than integrating 0, right? Maybe not integrating at all, but then that's not fun. Anyway, so again, you know what's coming next? I'm going to look for my pattern. So if I call this f, look, there it is. Because of my chain rule, there is f prime. And if I call this, well, if I call this G, then there is my G prime. So I can see my product rule. That's to me, that's like a green flag just saying, yep, you're good to go. So this is now the derivative with respect to time of the product 100 plus t cubed times, yeah, my unknown function, which is the amount function, right? And then let's still have a 0 here. So what happens is now, even though it's really easy, you can't forget your plus c. So again, integrating both sides, I will write it, right? So it will look like this. It's the integral of 0 with respect to t, but this would give me 0t plus c. So I end up getting 100 plus t to the third power times a is equal to 0 plus c. I'll just put my constant there. So look at what we end up with. So here is our general amount function. It's c over 100 plus t to the third power, right? Which is really interesting. And we have an initial condition, so let's see, when t is equal to 0, our A is equal to 15. Remember, there were 15 pounds in there of salt dissolved initially. So we have 15, and then at the bottom, what do we have? So yeah, basically 100 to the third power. So we have this, right? Which we could write as c over 10 to the 6th, right? So when you get like really big numbers, and sometimes you do, sometimes in these applications you get numbers that you don't typically have numbers of that magnitude, but you can always do it as in scientific notation. So this or something. Okay, so c is 15 times 10 to the 6th. Technically, this is not scientific notation because this factor here is not between 0 or 1 and 9. So if I wanted to make this technically scientific notation, it would be 1.5 times 10 to the 7th power. So there we go. And I'll leave it at this in this form. If you want to write out the numbers in the standard form, you're free to do that. But here now is our final answer. So the amount function, right? So at any given time, this function, the 1.5 times 10 to the 7th power over 100 plus t to the third power pounds, right? That would be the units here, pounds, will represent the amount of the of salt in the tank at any time t. And notice what happens as t gets larger and larger. This denominator gets larger and larger, but the numerator is just a constant. It might be a big constant, but over time, this amount function is going to approach zero, which is what we would want in the scenario I described earlier. If we're trying to flush this tank clean by pumping fresh water in, mixing it so it becomes completely homogeneous, and then pump it out, right? Over time, we would want that the amount of salt in the tank should become negligible, right? And once it hits a certain threshold, maybe a threshold that's set by, I don't know, the EPA to say, okay, it's not considered clean until this amount is there, or this concentration is left, then you have to keep the process going. If we wanted to find the concentration at time t, so let's state that. So the concentration, just so we can see that the two function, or I guess three functions now, right? Because we have the volume, we have the amount, and now let's write down the concentration. So the concentration of salt in the tank at time t is, concentration is always amount per unit of volume. So it's always the amount divided by your volume. So it would be, in this case, 1.5 times 10 to the 7th over 100 plus t to the third power, and then also divided by our volume function. But what was our volume function? Our volume function was 100, so it's this divided by the quantity 100 plus t. So basically I would have another factor of 100 plus t in the denominator. So here is my concentration function. I don't want to use, I guess we could technically use like C of t for concentration, but we would have to define it as the concentration in the tank at a certain time, not what's being pumped into the tank, because remember that concentration is zero in this particular problem. So we have 1.5 times 10 to the 7th, and then in the denominator we'll have 100 plus t to the 4th power. Now the units here will be pounds per gallon, right? So now we have these two really useful functions that can be used to determine lots of other things. Most of the other things that you will do in a problem like this are algebraic, right? So there you go. There's our one compartment analysis / mixture problem solved via differential equations. How fun. See you for more fun in the future.